Hi, my name is Kostya Osipov, and I'm a regular guest of these events. I don't know why they invite me, and because probably I'm such a fan of strong consistency. And today I'm going to talk mostly about Scylla 5.2, what we deliver there, but also about our future plans, what we deliver in the on the road to strong consistency in Scylla. So this presentation is structured as follows. First, I'm going to talk about 5.2. Consistent schema management, consistent cluster management. It goes generally available in this release. And I'm going to discuss how you upgrade, how you use it, what it delivers. Then I'm going to talk about 5.3. 5.3 is our upcoming release. I know that probably for you it's all new, but as I speak, we have branched off 5.2 and we are merging some exciting features into 5.3. So I'm also going to mention that. And then I'm going to mention stuff that comes after 5.3, like our future roadmap. And I know that you're probably familiar with all that, or maybe you're actually new to these shows. And in this case, I refer to the previous episodes of this. So there are excellent talks about internals. So this year, I'm not going to talk a lot about internals. I'm going to discuss what we have actually delivered. So there are these talks. They're available on Scylla Summit page on YouTube. So please go and watch them. There is like in-depth overview, in-depth review of what we do in strong consistency in Scylla. So first, also, for those who are new to the problem, let me define it real quick, and I will not go back to it anymore, I promise. So what is this whole problem of strong consistency? What is strong consistency versus eventual consistency? Why are we making advances on the path to having strong consistency in Scylla? First of all, consider these two illustrations, like how strong and eventual consistency queries are handled. You can see that strong consistency queries, they actually require acknowledgement before the acknowledgement is returned to the client. Eventual consistency queries against any kind of system, a database, a messaging system, whatever, they can proceed without full connectivity in the cluster, without acknowledgement from another node. So acknowledgement is happening afterwards, after the reply is sent to the client. As a consequence, you can see that strongly consistent systems, they require a majority to make progress. But on the other hand, they because they can acknowledge the write or the read, they know the latest state of the database before they return to the client. Eventually consistent systems are highly available. They don't require strong connectivity. And in order for the writes which happen, concurrently in the system to be making any sense, they need to commute. That's called commutative data types, commutative operations, so that the system can eventually build some order of all of the writes happening concurrently. And from like a real strawman, like a real simple perception of this would be of this problem would be that when you observe a strongly consistent system, it's like observing two people talking. It's but they are very polite. They are talking, taking turns, or there are probably many people talking. They happen to talk concurrently, but you see the events, the sequential flow events. One event strictly happening after another, and you can make sense what's happening as you observe. And with eventually consistent systems, it's like you can only eventually figure out what happened, and all of the events happen concurrently. Now let's turn to Scylla and how this all relates to Scylla. So Scylla, first of all, is a database from the Cassandra family, and Cassandra is an eventually consistent database, which means that it uses eventually consistent algorithms for many things. And if you look at what database actually stores, it stores data like rows, cells, maps, wherever, strings, and it stores metadata, the definition of the shape of the data. And the metadata in a database, as you can see, it includes schema information, the data types, what columns are there, their names. and the topology information, what nodes are present in the cluster and how the data is distributed among these nodes. So initially, like back in 2012 or wherever this all was created, eventual consistency was used for everything, for data and for metadata. But if you also take a look at this picture, at the illustration, you will see that metadata is actually shared by all of the nodes, whereas data is partitioned. So metadata requirements for availability are different than data requirements for availability. To make data available, you need to have like both replicas in this case available. And this is a strong requirement because you have just two replicas stored in a certain partition. For metadata, you need the majority of the replicas from the entire cluster to be available, which is, you know, you have to lose the majority of your nodes to make the system not available. So in most cases, you can make progress and you can make, you can do strongly consistent operations with metadata and still your system is going to be live. So you can also see that data is changed frequently, whereas metadata doesn't change that much. And it's not always commutative. So it makes all the sense to use strongly consistent algorithms for metadata. And this is what we do in Scylla. This is what we have done and what we will be doing more. And this is the big change we are taking from the original Cassandra design. So a while ago, we turned to Raft to implement the foundation for our strong consistency. Raft is actually a replication protocol. A replication is something like how you store records on multiple nodes, how you ensure that multiple nodes in the cluster have the same sequence of records in the log. So the way we use Raft is essentially we use that replicated log is by having the record store some kind of a program for our system. Like that program, like imagine you wanted to make something highly reliable and you want and available. Like you wanted to have certain program execute and tolerate a single machine failure or multiple machine failures. Imagine your program would actually be deterministic. So if it takes certain sequence of inputs, it produces the same sequence of outputs, regardless of like the actual timing and so on. It's what's important is that the sequences of inputs is the same all the time. So this is what we actually use for executing the changes on the metadata in Scylla. So it's the same. And metadata is a sequence of changes of like topology, of schema, and so on. So in order to make this program available, we first put that data into a replicated log. We make sure that the majority of the nodes in the cluster have the same copy of the log. And only once we have ensured that, we actually apply and execute these commands. So this is what gives us this durability and this linearizability, the same order of events, different nodes of the cluster. So big news, in Scylla 5.2, we actually ship our first major use of Raft, and we use it for propagation of schema changes. As I'm preparing this talk, we've branched off Scylla 5.2, and there is a new option called Consistent Cluster Management, and it delivers safe schema changes. If you perform concurrent schema changes, you know there is no shadowing of the previous definition. The schema changes no longer commute, so they no longer have to commute because they execute in the same order on all of the nodes. And so there's no data loss, there is no shadowing of the old definition, and the schema changes also have become much faster, meaning that currently, because of Raft, Raft has actually dedicated leader responsible for pushing the changes across the cluster. So schema changes can now propagate much faster than they used to when they were using Gossip. So one drawback of that change, though, that if a node is partitioned away from the cluster, or it's probably an advantage, depending how you look at it. If a node is partitioned away from the cluster, it can't perform schema changes anymore. If you lose the majority in the cluster, you can't perform schema changes. So an important part is, of course, that data path is not affected. If you lose the majority, you can still perform the writes and reads from partitions. But still, when we ship this, we're preparing for shipping this, we wanted to make sure that the system, we have a recovery path even for a disaster scenario. So let me talk about it a bit more. First, let me say that Raft is on by default in all our new clusters. So a Scylla YAML now contains a setting called consistent cluster management, and it's true by default. For clusters for which you perform an upgrade is going to be, of course, the old Scylla YAML file, so you're going to have to turn it on explicitly. We recommend turning it on, and in future releases, it's going to be turned on by default. If you are upgrading, there is a special procedure that would carefully collect the full cluster, make sure that the schema is the same on all of the nodes in the cluster, synchronize the schema, and then enable consistent cluster management across the entire cluster. So you can turn the feature on, then perform a rolling restart, and you are going to have it in the clusters, which like pre-existing clusters. And here's the QR code you could use to go to the link in the ScyllaDB manual that gives a lot more detail about how you actually use this feature, what are the possible drawbacks, and how you work things around to, to even save clusters which lost the majority. So I've been mentioning this many times. Let me just reiterate it one more time and highlight the procedure for recovery. If your cluster is if you have a split brain situation, if most of the nodes of your cluster are gone, how you can salvage what's there, and create a new cluster from the remains. So first of all, if you have a 3 data center setup, if you have a single data center setup, this is probably something you will never need, because it's really a rare situation when you permanently lost the majority or permanently have a split brain situation. It's like your entire data center and a 2 data center setup is gone. But here are the steps that you take to actually recover the cluster. And the basic idea is that you drop the consistent state on every node and recreate a new cluster from the remaining nodes, so they create a new consistent state from the data that is available to them. You need to perform a couple of restarts. You need to make sure that the dead members are isolated so that they never can disrupt this new cluster. And after that, you're good to go. And this is, of course, also part of our manual. So please go to the manual and follow the steps, try it out, and let us know what you think. Maybe with issues, maybe with just feedback, and so on in the forum. Another feature we delivered in Raft before shipping it, before making it generally available, is the IP change support. And here the problem is also very similar, because there are environments like Kubernetes environments. When nodes restart with different IP addresses, preserving their persistent state. And this can happen dynamically. This can happen without any control from the DBA and so on. So in case this happens, there is a good degree of automation. So what happens is actually the node, which if only a few nodes in the cluster change their IP addresses, so they still know some of the old IPs in the cluster, they begin talking to these existing nodes, and they learn the rest of the IP addresses, and they share their new IP addresses. We still continue using Gossip for that. So Gossip is a subsystem that starts first in Scylla, and before we can make any connection to the majority, we need to figure out the IP addresses. So we propagate this information through Gossip, and then a Raft can deliver messages to these new nodes, and they join the majority, and things are fine. You can also change IPs of the entire cluster. So you can restart the entire cluster with the complete set of IPs changed. It's not something we recommend, but at least Raft supports that. So in this case, you need to update your Scylla YAML and list the new IPs in the seeds section of the file, so that at least the nodes can connect to the new IPs and again exchange this information, and then Raft is going to get updated, and the system peers is going to get the new information about the new IPs, and your cluster will be available again. So now with that, like this, what comprises the features we ship in 5.2. I again encourage you to take a look at them. And now let's talk about our new work, which is still experimental, but it's already materialized in our trunk. And I hope it's going to go out in experimental mode in 5.3, and we will mature it throughout 2023. You know, there are always these forward-looking statements which you should avoid, but I guess that's still good to share so that you know about our plans. So first of all, what are we actually doing in 5.3 and what limitation we aim to address with our work? We are taking the next step. Apart from the consistent schema changes, we are trying to address and make the topology changes also use the highly available, strongly consistent Raft store. And I would like to mention that Cassandra community has also recognized the problem, and there is now a Cassandra PEP, and you know, this makes me very happy because it means that we are not doing something, you know, crazy. The Cassandra PEP called or SEP actually, it's called SEP, Cassandra Extension Proposal, transactional cluster metadata, and it lists all the same problems which we are trying to fix. First of all, we want to make sure that topology operations can be started concurrently. It's not always viable to guarantee what Scylla and Cassandra manuals recommend today, like you only run one topology change at a time. So we want to make sure that even if you start concurrent topology changes, you can still safely perform them. So the cluster is determining the order of these topology changes and doing them for you. Second, we want to make sure that the failure during the topology change doesn't lead to a data loss. And there are two kinds of issues here. First of all, the main issue actually is coming from the nature of how tokens, the new tokens, are propagated across the cluster. Currently, they use gossip to propagate across the cluster, which is, of course, not reliable. It's dependent on time, and there are some timeouts to like just stop waiting for gossip at some point. So it's entirely possible that some of the nodes in the cluster, they don't see the new tokens, and some already see it. So you have a scenario when read and write quorums for the same data are actually different, which can lead to a data loss. Or you can have a scenario when you use different write quorums, and then you don't use repair. So the quorum guarantees for your writes are not actually satisfied, even though you have a successful response from the database to a quorum write. So these issues, they are also gone basically with the new consistent cluster management, consistent topology management. And the third problem, and I've already mentioned it a bit, like I said, that the gossip has to wait for like 30 seconds for the new tokens to propagate. We no longer need to wait for the tokens to propagate. And I'm going to explain later how we actually achieve that, so we don't need to wait, because there can be requests in flight which are using the old topology, and you can't guarantee like you have drained all of these requests. Like generally, you can't guarantee it. There may be some, long-running queries which are still based on the old topology. So you need to wait. And I will explain how we reduce this wait to a minimum. So first of all, how we did it. Like same as with consistent schema management, we put this information about the topology into Raft, into this thing which is called group 0. Group 0 is the first Raft group we are going to use, and we are going to have many groups in the future. But for now, we have this main group, which includes all of the members of the cluster. So this information is now replicated through Raft. And it's now entirely possible to avoid the situation of this, having stale topology. No nodes, they use stale topology now because they always get it quickly through Raft. The second thing we did to achieve that is we switched to a centralized topology change algorithm. And by centralized, I don't mean that there's like the single node which is doing all the changes, but there is a single coordinator running at a time in the cluster, which is capable of performing the topology changes. So how this works? Raft is a leader-based distributed algorithm. So at any point in time, there is only one leader who can. There can be other leaders like deposed leaders, but there is only one leader who can actually change the linearizable state in the cluster. And alongside this leader, we run a special process which performs the topology changes. This process is highly available because if the leader changes and this process fails, it's going to restart alongside the new leader. This process is responsible for driving the topology change progress forward. So if previously the node, which is like joining node, or the node that is performing the node tool request, would be driving the topology change forward. So if that node fails, the DBA would be responsible for finalizing the process, for aborting the process, for cleaning up. Now, this centralized coordinator is responsible for driving that process. And since the centralized coordinator is highly available, now we can fully automate the topology changes. Like even if this node, which we are trying to add, fails, the coordinator can finish the work and it can abort the adding of the node. And if previously, like I said, the data was propagated through gossip and the commands were performed by the nodes as they learn information from gossip, now the topology, like what sort of commands, like start streaming, stop streaming, begin routing rights to the new replica, and so on. So this kind of commands. So they were replicas would just execute them as they learn the new information through gossip. Now the coordinator is sending these commands explicitly, so it happens much faster, especially if your cluster is small. If you're just starting a new cluster and rebalancing it, you can actually start the nodes really quickly. And finally, I would like to mention that even though we changed this to use this sort of centralized coordinator, of course, the data path is again unaffected. So the data path uses the local state of topology, and the coordinator is responsible for driving the process in a way that the local state of topology on every node is consistent. So like when you perform streaming, for example, you make sure that your writes go both to the old and the new replicas for a while, and only then you switch the writes to the new replicas. And this is how it looks from like a time perspective. So if previously, if you add multiple nodes at a time, or if you add just node C after you added node B, and node B happens to be down, node C might not see node C might not see the token metadata of node B. Now this changes the token metadata. They're linearizable. So node C, when it bootstraps, it always can see the token metadata of node B and node A. So it's strictly sequential. And I also mentioned that we perform the automatic coordinator failover. And this, of course, is necessary when the node which is driving the topology change dies. So how we do it? We have a sort of a special failover takeover messages in the cluster which instruct the nodes to sort of stop accepting commands from the old coordinator, and now you need to only accept commands from the new coordinator. And this is only after ensuring that the nodes have received these commands, we can drive the process forward. But also the new coordinator is guaranteed to have the same state of the token metadata as the previous one. So it's going to resume the process from the same point which is left unfinished by the previous coordinator. So all of this becomes possible thanks to Raft. We also had to perform an important change in the data plane to make the topology changes quicker and safer. And we call this feature fencing. So let me explain what it is. Now, if previously we were relying on a timeout to make sure that the old writes drain out from the system, now we have the coordinator control this condition. So one thing the coordinator does is it sends a fence request to all of the replicas in the cluster to stop accepting new requests which use the old topology. So if there is some node which is not part of the majority at the moment, which is disconnected from, say, coordinator, but probably is able to reach to some of the nodes in the cluster and send queries to it. So if this node is sending these queries are signed with the topology version that this node is aware of at the moment. So it's going to be a null topology version. And these queries, they're going to be fenced, which means that they're not going to be accepted into the system. At the same time, the coordinator is waiting for all of the queries on all of the live nodes to dry out, to drain. And only after this happens, it switches to the new topology. So you can see on this diagram like that how this actually works. So there is a request from the right coordinator, which is the second arrow on the diagram, and the right coordinator, the first request from it is actually in the system, so it's allowed to finish. But the second request from the same coordinator, which happens to use for whatever reason, and null topology is not accepted into the system. At the same time, when this happens, probably over time, this node, it learns about the new topology and sends a new request with version 2 topology. And this request is accepted into the system all right. It runs concurrently with the first request. And we switch completely to the new topology as soon as the old request drains. So you see the yellow arrows, they reflect the drained requests. So I would like to summarize about what we are actually delivering in our upcoming release. And this is, first of all, we allow requesting multiple concurrent operations. This is the first step to performing these operations concurrently, and this is going to come with tablets. Second, we are now are able to check and not accept incorrect operations. So if there is an operator error, if you try to say replace a node which are currently removing, and you are trying to do this concurrently for whatever reason, we are now able to see it because there is a centralized state, there is a linearizable state, so we see all of the requests in the same place. And we are able to produce a meaningful error message, not just blow up the cluster in this case. Then if a node dies, the coordinator, say which node we are adding or removing or replacing or whatever, the coordinator can notice that. And there is this concept of abort of this topology change. So this abort is being driven by the coordinator, not by the DBA. So it's automatic. And finally, the topology changes are going to be safe and fast. Like safe meaning that because of fencing, we are not going to permit the situation with when read and write quorums disagree. And fast because of fencing, we are not going to wait for this gossip timeouts like 30, 60 seconds for the old request to drain, because we can actually track and continue with the topology change as soon as they drain out. So in a healthy cluster, this is going to happen real quick because the nodes will learn about the new topology quickly, and the old requests will be finished quickly. So we will be performing these changes also quickly. But this is not the end, right? So after 5.3, we have a whole new roadmap. And before I touch on this roadmap, I would also like to mention one experimental feature we ship in 5.2. We don't recommend using it like in any production environment, but it's a nice feature to play with. So what it delivers is what we call strongly consistent tables. Right now we have just one strongly consistent table, but it already provides a preview of what is possible. So what it delivers is that you can now perform a strictly linearizable update. So you probably know that the semantics of SQL in Scylla is commutative. So you can update a record which doesn't exist. You can perform two updates concurrently, and they're going to the latest update is going to win. In this case, you are going to get a strict order of all of your updates, and your update, it performs actually the read of the previous value before it performs the write. It's similar to lightweight transactions, but the difference is huge, and the difference is in the underlying implementation. The underlying implementation is using Raft, is using leader-based. It's much faster because it's only using 2 round trips to commit a change. And it's also it's also extensible to a way more broad semantics than what is provided by lightweight transactions. So we plan in 2023 to also extend this feature and provide these strongly consistent tables which are replicated everywhere, and give more syntax basically for working with them. Why do we do that? If you look at our roadmap for delivering strongly consistent storage in Scylla, you will see that there are many like stepping stones to get there. We delivered Raft in 5.0, and this was only an experimental feature with experimental schema changes. Then we made the schema changes stable in 5.2. We are shipping the safe topology changes in 5.3 or whatever is the release that is coming. And then we are building the consistent tables. The consistent semantics allows us to later on just change the partitioning scheme for this kind of tables, and we get all the same queries running in a distributed storage. So finally, we need to build that distributed storage. So we are building dynamic partitions, or like tablet partitioning, which we call tablet partitioning. And finally, all of this combined will deliver this flexible, highly manageable, strongly consistent storage in Scylla. With that, I complete my presentation. Thank you very much. I would be glad to, if you get in touch with me and provide your feedback. Thank you again.